Good day, ladies and gentlemen. You are welcome to our second lecture on Cmen843 Semiconductor Microelectronics. And the first slide you are seeing here is the picture of myself, Engineer Kabir Ahmad Abu Bilal, the lecturer of this course, because some of you have never met me, and for this reason I think it is good to maybe give you some information like this. So if you remember what we have done in the first lecture, we revised generally on semiconductor microelectronics, where we talked basically on intrinsic semiconductors, meaning those semiconductors that are in their pure form without introduction of any impurity into them. Today we are going to look at what we call the extrinsic doping, and this is nothing but a process of introducing some impurities into pure semiconductors in such a way that we can change their conductivity. And you know, we introduce either group 5 if we want to get n-type semiconductor, or we introduce group 3 if we want to get p-type semiconductor. So here we are saying if we introduce a little amount, that's the meaning of shallow level of impurities, of phosphorus, which is a group 5 element, if it is introduced into the silicon, so 4 out of its 5 valence electrons will now enter into the silicon bonding, and it will share 4 with the 4 neighboring silicon atoms, while there is 5th electron which is unattached to any atom, that is, it is delocalized, and this electron is free to move from a place to place in such a way that it is no longer in the valence band, but rather it is in the conduction band. And by doing this, if you introduce group 5 element where you have an excess electron, we say we have donor states. The phosphorus itself, it is called a donor atom, and the condition of that silicon to which phosphorus is introduced is called donor states. And whenever you increase the temperature from absolute 0, that is minus 273 degree Kelvin, if you introduce the temperature to around 100 Kelvin, it will give enough energy to this electron, that is the 5th electron which is not bonded to any of the atoms. It will give it enough energy to now start moving from where it is into the conduction band, and this electron will now become physically separated from the phosphorus atom, and for this reason it is mobile. So the amount of energy that is required for ionizing electrons from the phosphorus is small compared to this band gap energy, which means since the electron is already mobile, so we require a smaller amount of energy for us to finally push the electron into the conduction band, and this energy is proportional to the thermal energy, which is given by kT. We know K is Boltzmann's constant and T is the absolute temperature in Kelvin. So for this reason, whenever you introduce a small amount of group 5 impurity like phosphorus into the pure semiconductor like silicon or germanium, the conductivity will increase. And I have already told you, or I reminded you, you know this. The reason is that we have 5th electron from the impurity which is not localized, which is not attached to any of the atoms, and it can easily be pushed into the conduction band. Now if on the other hand, instead of introducing group 5 element, you decided to introduce group 3 element like a boron. Boron is a group 3 element. It has 3 valence electrons. So if it enters into the silicon or germanium, it will share these 3 electrons with 3 out of the 4 neighboring silicon or germanium atoms, which means there is one place, one atom of either silicon or germanium that will not get a pairing electron from the boron, because the boron has only 3 while the neighboring atoms are supposed to be 4. So in this case, the place where that electron is missing, we call it a hole. A reminder, everybody's supposed to know this. And in this case, we are in a condition that we need one additional electron, and for this reason the boron is called an acceptor, and this condition of introducing it into pure semiconductor, we call it acceptor states. And just like the introduction of group 5 elements, whenever you increase the temperature to around 100 degree Kelvin, the vibrations will start taking place, and the energy of the silicon lattice will easily now promote that place where the electron is missing. It will now produce, or it will promote that electron to move easily into the conduction band, because it is not physically connected to any of the atoms. So in this case, we will say that the atom of boron that has 3 valence electrons is having what we call a hole, and as I have said, it is called an acceptor because it needs 1 electron to fill that gap. And the amount of energy required for it to move into the conduction band is also proportional to the thermal temperature, which is kT. K, Boltzmann's constant, and T, the temperature. So the presence of this hole, that is a place where electron is lacking, is also responsible for increasing the conductivity of the pure semiconductor like silicon. And in this case, we have 1 electron lacking, and I said that place is called a hole. So the hole is like a positive because electron is what? Negative. When the hole and electron are mixed together, they will cancel one another because the hole is positive while the electron is negative. So in the case of introducing group 5 element, we create what we call N-type, that is negative type semiconductor, because we have excess electron which is negative in charge. But in a situation where we introduce group 3 element like a boron, we have a hole, and that hole is positive, so we call that semiconductor p-type semiconductor, which means positive. Now, this introduction of either group 3 or group 5 is the fundamental mechanism of extrinsic doping. That is a process of introducing an impurity into the pure silicon or germanium in order to create N-type or p-type, and all of them are responsible for increasing the conductivity. And whenever you have, as I've already said, a semiconductor to which you introduce group 5 elements, we call that one N-type semiconductor, and if you introduce group 3 elements, we call it p-type semiconductor. Now, if we want to consider the compare the extrinsic and the intrinsic semiconductors, we've already talked about the pure semiconductors, which we call intrinsic, and now we discuss about extrinsic. Now, whenever you multiply the number of electrons with the number of holes in intrinsic semiconductor, you are going to have Ni square, where Ni is the intrinsic concentration. It can be electron and it can be a hole. And we have seen in our first lecture that N times V, or Ni square, is given by NV NC exponential minus Eg all over kT. And this one is applicable also to extrinsic semiconductors. But as I've already told you, if you introduce group 5 elements, the number of negative charges will be more than that of the positive. But if you introduce group 3, the number of positive will be more than that of negative. So therefore, we no longer use Ni square because P is different from N depending on which impurity is introduced. Also, a semiconductor, whether it is extrinsic or intrinsic, it has to be electrically neutral, and that is achieved by saying P minus N plus Nd minus Na equal to 0, where P, number of holes, N, number of electrons, Na, number of donor impurity, that is group 5, Na, number of what? Acceptor impurity, which is group 3. And if you combine these two expressions, the first one here and the second one here, you are going to come up with these expressions for the concentration of electron and for the concentration of the hole, depending on whether we introduce N-type or a p-type. Now this Nn and the Np, they are majority charge carriers. Nn electrons and pp holes. So the quantity Na minus Nd is what we call the net impurity concentration. That is, if you say Na, the concentration of the acceptors, minus the concentration of donor, it will give you net impurity concentration. So in a situation where Na minus Nd is equal to 0, where it vanishes, whenever it becomes 0, now you find that N and P are equal to Ni, the intrinsic. And how do we prove this? Go back to this expression. Whenever under these square roots, Nd minus Na becomes 0, and here also Nd minus Na becomes 0, you will be left with a square root of 4n squared, and that will give you 2Ni, and this half will cancel that, therefore Na is equal to Ni. The same thing here, when Na minus Nd is equal to 0, we will be left with square root of 4Ni squared, and if you take the square root, it will give you 2Ni. Multiply by this half outside the bracket will give us Pp equal to Ni. So in a situation where Nd minus Na or Na minus Nd is equal to 0, it means we don't have any donor, and therefore it is purely an intrinsic semiconductor. So such semiconductor, as I've already said, it is intrinsic, and the doping is said to be wholly compensated, meaning the doping is not used in this case. Or even if in a situation where you introduce acceptors and donors of the same magnitude, so one minus the other will cancel out, and the semiconductor will now start behaving as if it is what intrinsic semiconductor. But in a situation where we have partial compensation, that is, if the donor and the acceptor impurities are in different quantities, therefore Na minus Nd should not be 0. Likewise, Nd minus Na will not be 0. So in this case, our semiconductor, it is intrinsic in nature, and in practice, the concentration of this dopant is introduced in such a way that it is much in number compared to the concentration of the intrinsic semiconductor. And for this reason, you find that in introducing group 5, we'll be left with Nn equal to Nd minus Na. That is donor minus acceptor. But if we introduce much of group 3, that is acceptors, the expression should be Pp equal to Na minus Nd. So in each case, the minority carrier concentrations Pn or Np, that is, if you look at this one, we said we introduce donors more than what? The acceptors. Therefore it is N-type. So in this case, the minority carriers should be Pn. It is N-type, but still we have holes, because whenever temperature starts rising, bonds will be broken and definitely holes will be present, though they are much less than the electrons, and therefore they are the minority charge carriers. And also, if you have more of Na minus Nd, that is, it is an acceptor, we introduce much of group 3, you find that even though this Pp is the majority, you will find that there is Np, which is the minority charge carriers in that sense. And in this case, you find that whenever you multiply the minorities in the N-type times the majority, which are the electrons in the same N-type, you find that is equal to Pp times Np, that is majority in the P-type multiplied by what? The minority in the same P-type. That will give you an I square, and that is mass action law we introduced in our lecture number 1. So in each case, you will find that the concentration of the minority charge carriers is much less than the majority charge carriers, either it is N-type or P-type. And the impurity that satisfies this condition is that the net impurity concentration, that is difference between Na minus Nd or Nd minus Na, we expect the difference to be above 10 raised to power 12 centimeter per centimeter cube. So in practical doping, whether introducing group 5 or group 3, you find that the concentrations are much larger than this. So in that case, if you introduce much of group 5, you find that electrons dominate everything, though we have holes as minority. If you introduce much of group 3, the holes will dominate, even though we have some electrons as the minority charge carriers. So since the occupancy of the electron states for the crystal is always altered if you introduce either group 5 or group 3, the Fermi level in a doped semiconductor can no longer expected to be at the mid point. You should remember in our lecture number 1, we have seen that Fermi energy EF is found always around 50% of the band gap energy. But now, since you have made electrons more than holes in n-type, or holes more than electrons in the p-type, that position of the Fermi energy to be at 50% is no longer applicable here. So in this case, if you take the ratio of the charge or the carrier concentration, that is the ratio of the holes to the electrons, you find this expression. We have already seen this. P is equal to NV this, N is equal to NC this in our lecture number 1. Please, you can revisit it and confirm. We have already seen this expression. Now with this, we can now see, for convenience, if you take the natural log of both sides from this expression, you find that you have this kT over 2 ln of P over N equal to EC plus EV all over 2 plus kT over 2 ln NV over NC minus EF. So if you look at the first two terms here, these first two terms, this and this, on the right hand side, they stand for our Fermi energy level in the intrinsic concentration. Remember, this is discussed in the lecture number 1. And this expression, the first one and the second one, we call them the intrinsic Fermi energy. And we can remove these two and represent it by EI. And this expression will now be kT over 2 ln P over N equal to, instead of all these two terms, I will put EI. That is the Fermi energy concentration in intrinsic case, minus EF, which is the Fermi energy now for the extrinsic case. Now, the majority carrier concentration is determined by the dopant, that is the amount of impurity introduced, whether phosphorus, group 5, or boron, group 5, or any of the group 5 or group 3 elements. And if you want to obtain the expression for that carrier concentration, you will take what we call the carrier equilibrium, and this is given by these two expressions. Gentlemen, maybe, and ladies, look at these expressions, and of course the previous one I have seen here. The essence of this course is not to derive the mathematical expressions, but to use them in explaining some phenomena. So don't disturb yourself about how is this thing derived. If we take time to derive it, you may end up understanding nothing. So therefore, for n-type, this is the expression that we use to find our carrier concentration, and for the p-type, this is the expression we use. Now, the net impurity concentration for, is expected to be far above the intrinsic concentration, that is in the doped one, where we introduce either group 5 or group 3 element. So if we wish, we can go back to that expression and simplify it. Let's come back here. If you assume ND minus NA is much bigger than NI square, so it means you can make this one to be equal to 0, because this expression is assumed to be much bigger than this. And if you do that, you neglect this one and make it to be equal to 0, you will be left with square root of what? ND minus NA square. The square and the square root will cancel out. So you will be left with kT ln of ND minus NA plus another ND minus NA. And of course, that will give us 2ND minus 2NA. Factorize the two and cancel it with this one on top. So your expression for n-type semiconductor will be like this. We have minus kT ln nd minus Na over Ni equal to Ei minus Ef. That is, if we assume this Nd minus Na is much bigger than Ni, so we neglect this one, and finally our equation will be simplified to this. And if you do the same thing for the p-type, this is what you are going to get. If you assume Na minus Nd is much bigger than Ni square, so you let this one to be equal to 0, so you will be left with square root of Na minus Nd all square. The square and the square root will cancel out, and you have Na plus another, Nd plus another. You factorize 2 and cancel it with this one, and for this you have your expression simplified to this. Okay, so in this case the Fermi energy Ef is greater than the intrinsic Fermi energy Ei, and because of that, if you want to make this Fi the subject, take it to convert this this way, we will be left with Ef equal to this one Ei plus this. So which means this Ef is greater than this because it is equal to this plus this in the case of what? N-type semiconductor. But in the case of p-type semiconductor, if you take this Ef to this side and take this one to that side, so Ef should be equal to this minus this term, which means Ef is less than Ei if you are talking of what? The p-type semiconductor. And this is illustrated in this diagram where we said Ef for the n-type is above the Ei. Look at the diagram. This is my Ei, the intrinsic Fermi energy, and this is my real extrinsic Fermi energy. Ef, it is above what? This, based on the equation I've just discussed. But in the case of p-type, we see Ef is less than Ei, therefore see it below the bar. And also the Fermi energy concentration for the intrinsic case, either p-type or n-type, depends on the temperature, because whenever temperature increases, there is increase in the breakage of bonds, and that will increase the majority carriers as well as the minority carriers. Now at high temperature, when the temperature is very high, you meet or you come to a point where the thermal excitation, that is breakage of the bonds due to increase in temperature, is now dominant compared to the extrinsic impurities we introduced. So in this case, you find that the majority carrier concentration will begin to increase exponentially. And if this continues, you find a point where this temperature will make the extrinsic or the external impurities we introduce, they will be negligible, because the more the temperature, the more the breakage of bonds, so that the minority and the majority will tend to be equal to one another. So in this case, when the temperature goes beyond that limit, it becomes effectively intrinsic, because the effect of the dopant, that's the impurity, is not noticed very much. So if we take the difference between the intrinsic Fermi energy and the extrinsic Fermi energy, we can express it as what we call equivalent electrical potential. That is, this phi f is equal to the absolute value of Ei minus Ef. Ei for the intrinsic, Ef for the extrinsic, all over what? Q, where the Q is an electron charge, which is 1.602 times 10 raised to the power minus 2 coulomb. Now, if we come to carrier mobility, we have already seen that whenever a charge carrier, whether electron or a hole, is delocalized, that is moved from the valence band into the conduction band, it will start moving because it is free. So for this, we expect the movement of that charge carrier to bring about increase in what? The amount of current to increase. Because what is a current? Current is equal to charge all over time. That's the flow of charge over time will give you the amount of current. Okay, so whenever you have a high concentration of mobile carriers, the electrons or the holes, you expect the current to start rising. But if you have your carriers in crystalline conductor at room temperature around 25 degrees Celsius, you find that those electrons which are delocalized, or the holes, they will be moving randomly. They will be colliding with one another without a specific orientation. Just like the smoke, the movement of smoke is a random motion. It doesn't have any pattern of movement. So in this case, you find that whenever you increase the temperature, the randomness of these charge carriers will also increase. And for this reason, if you didn't introduce any external electric voltage, if V is equal to 0, you find that the carriers are not moving in a specific direction, and for this reason, no current is expected. But whenever you apply external voltage into this semiconductor, it will now align the free mobile charge carriers, electrons or holes, and they will start moving in the same direction. And this will create some amount of what? Currents. And these mobile charge carriers, whenever they are moving in a given direction, they definitely have what we call a draped velocity. Okay. It is also possible for us to estimate that draped velocity. We talked about when applied potential has aligned all the charge carriers, electrons or holes to move in a certain direction to give a current. And for us to be able to estimate that force or the velocity, we have to use the formula for calculating the force, that is Newton's second law of motion, which says F is equal to ma, that is force is equal to mass times acceleration. And also we should remember that the force on a charge is equal to this charge times electric field intensity, that is E. So now we set QE, which is the electric force, is equal to m times dv dt is our acceleration. So when this applied field, that is the voltage, is constant, then we can integrate this relation to come up with the formula for the velocity. Here, this our dv, when integrated, will give us v, which is equal to QE all over m, that's the mass, times dt. dt is now the time period during which that electric field is applied. Now, from that formula, we can see that the drift velocity when the field is applied and the field is constant, we call that carrier mobility. That is the speed with which that charge carrier, whether electron or hole, is moving. And the hole and the electron mobilities are specific properties of a particular semiconductor, which means the mobility of holes in silicon is different from that of the germanium, is different from other semiconductors. Each semiconductor material has its specific draped mobility or velocity, that is mobility. And also we should understand that this formula for calculating the draped velocity is applicable only when the electric field we apply is relatively low, less than 1000 volts per centimeter. If the field intensity is more than that, this formula is no longer applicable, because at such high voltages you attain a point where the velocity becomes constant, and we call that constant velocity saturated draped velocity. But whenever the field intensity is less than 1000 volt per centimeter, we should expect that formula to be accurate. And this fact we have talked about, that when the field intensity increases, the velocity tends to become constant. Look at this graph. If you look at this graph, you can see that the vertical axis is for the velocity, while the horizontal axis is for the field intensity. And you can see that here is 10 times 10 raised to power 6. Now, if you look at this carefully, you see that the field intensity or the velocity for the hole, for the electron rather,
given by this first curve, it becomes constant at this point, and if you trace it, it will give you around 8.5 times 10 raised to the power 6 centimeter per second as the velocity. And this curve, the other one, the lower one, is for the hole. And at this point where the electron become the velocity for the electron become constant, that of the hole also becomes around that value constant. But if you trace it, it will be around 4 point something, which means it is around half of that of electron. So which shows that the mobility for electron is higher than that of what? Hole. Now, if you consider a current I, if we assume we have a rectangular crystal of a semiconductor which is heavily doped with n-type semiconductor, that is with group 5, the value of the current that will be produced is given by this: I equal to minus Qn V A. Q is the charge of electron, N is the concentration of electrons, and V is this draped velocity we talked about, and A is the cross-sectional area of that rectangular crystal. And you can remove this V and replace it with this, that is our Qn is here. Instead of putting V, we put mu E dV dL, and our rectangular area is still there. Okay, so if we assume a rectangular crystal, as I have said, and which is doped with n-type, that is group 5 elements, the current I is equal to Qn VA, where Q is the charge of electron, N is the number of electrons, V is that draped velocity we calculated, and A is the cross-sectional area. If you wish, you can remove this V and replace it by mu E dV dL. And this mu E is the mobility of the electron, and the dV is the potential applied, L is the length, and of course A is the cross-sectional area. So from Ohm's law, if you want to express the resistance, you know that resistance is equal to voltage all over current. So your dV here is the voltage, and I is the current. Now if you make dV all over I, the subject, you will come off with 1 over Qn mu E times L over E. Just try it from here. Make dV all over L the subject of this formula. You come up with this expression, which stands for the resistance, that is for the n-type. You can have the same expression for the p-type, for the holes, which means this Rp is equal to 1 over Qp. Instead of n electron here, we put p for the hole. Mu E should be replaced by mu H because we are dealing with the hole, times what? L over A. This is the expression for the resistance. And if you want to get the overall resistance from both the electron and the hole, add these two formulas we talked about, you come up with this expression. And you also need to remember that the resistivity of any material is equal to Ra all over L. That is resistance times length of that thing all over the cross-sectional area. From here, if you multiply this R times this A and divide by this L, it will give you this as your resistivity, meaning rho is equal to 1 all over Q into N mu E plus P mu H. And if you look at this one clearly, the resistivity of any material is function of its carrier concentration, because this mu E and the mu H, they are constant for any semiconductor material, as we have said, but the N is a variable and the P is also variable, so they are the properties, or they are the parameters that determine the resistivity of any semiconductor material. And we also need to remember that resistivity is reciprocal of conductivity. Everybody knows this. So whenever the resistivity of p-type semiconductor is expected to increase, it is expected to be higher than that of what? The n-type, because the mobility of electrons is more than that of what the holes, and for this reason the p-type should have more resistivity compared to n-type, which have the same dopant concentration. And whenever the net impurity concentration increases, we should expect that the resistivity should what? Decrease. Due to what? The increase of majority charge carriers. Now, if you want to, so if we look at this graph, the lower one is for the n-type and the upper one is for the p-type. You can see that on the horizontal axis we have impurity concentration, and on the vertical axis we have resistivity. And this graph is telling you that whenever the impurity concentration increases, the value of resistivity of either n-type or p-type semiconductor will decrease, just like what we have just stated. So at ordinary room temperature, the dependence of the contribution of the lattice scattering, what we mean by lattice scattering is a kind of defect that happens in semiconductors. We are going to discuss that one in more details later in our future lectures. So when this contribution of the lattice scattering to the mobility of carrier at ordinary temperatures, the formula is given by this, meaning mu xl of t equal to mu xl of t naught, where t naught is the initial temperature, maybe you can take it as the room temperature, times t naught over t, where t is the temperature at a point where we are calculating that dependence of the lattice scattering of semiconductor mobility. And if you look at this, it's raised to power gamma, where this T naught, as I said, is the initial or the reference temperature, which is around 300 degree Kelvin, which is just like room temperature, 25 degrees Celsius. Now the value of this gamma, the power here, is approximately 3 over 2, which is 1.5, and sometimes it reaches even close to 2, but it is within this range. So this formulation is reasonably okay. It is okay for impurities concentration which is below 10 raised to power 18 per centimeter cube. Any value of concentration more than this 10 raised to power 18 per centimeter cube, this formula will not actually fit it. And also the expression for the resistivity as a function of temperature, because we know whenever temperature increases, the breakage of bonds keep on increasing also. So therefore temperature is a parameter that affects the resistivity, and that formula is given rho of T equal to 1 over Q nx uxl of T naught times T all over T naught raised to power gamma, then plus this, where this Q, everybody knows, is a charge of an electron, and is either the concentration of holes or the concentration of electron, because we put X here. That X can be hole and it can be electron. T naught is the reference temperature, which we said is around 300 degree Kelvin, and this C is a parameter which is with respect to the monotonic increasing function of temperature. What do we mean by this? C1 is a function of the material we are talking about. So now, if this C1 vanishes, meaning whenever it is equal to 0, you can see that all the function here also become 0. Then we are left with the function here, the first function after the equality sign. So if this C1 is not 0, then the resistivity may reach a minimum function at some finite temperature. Whenever it is 0, we don't expect the resistivity to decrease to minimum. But if it is not 0, then the resistivity can keep on decreasing until it reaches some value within a finite temperature. If we say finite, is a temperature which can be measured, but if it is into infinity, then something else comes in. So if you want to determine that temperature, we only differentiate this function from this function. When we differentiate it with respect to the temperature, we can get the expression for that temperature. And if you do that, you get this. d dt of rho of t is equal to this. If you differentiate that function with respect to t, just remember your differentiation function of a function, you will reach this point. Now if you equate this one equal to 0, that is the turning point, because whenever you say the derivative equal to 0, you are at a turning point where you can get the maximum or you can get the minimum. Just remember your calculus at undergraduate. Now if you equate that expression to 0, the minimum value of the temperature will be given by this function. Okay, just try it, though I told you the essence of the course is not mathematical derivations, but nevertheless, whichever facts I present, I encourage you to see how you can remember your previous knowledge and validate it. So whenever the temperature is low, this C1 is very large, so that the minimum value of this temperature will be greater than 100 degrees Celsius. And in this case, the resistivity of this material is dominated by ionized impurity scattering. What we mean by ionized impurity scattering is that the temperature is used for breaking the bonds, where it creates a pair of charge carriers, electron and what? The holes. Whatever number of electrons are created as a result of this ionization is equal to the number of what? The hole produced, because it is those positions where the electrons are removed that we call the holes. So in this case, the resistivity will decrease with temperature. Whenever temperature increase, the resistivity will start decreasing. And any semiconductor that exhibits this property, that is the decrease in resistivity as temperature increases, we said it have a negative thermal coefficient resistance. Negative because while the temperature increases, the value of resistivity is reducing, so it has negative thermal coefficient of resistance. But at a higher temperature, when the temperature is very high or lower dopants, either the temperature is high or the concentration of the introduced impurities is very small, the lattice scattering now dominates the resistivity. So in this case, the resistivity rho will increase whenever temperature also increase. So in this case, we call that semiconductor to have positive temperature coefficient, or we call it normal temperature coefficient. So gentlemen, and maybe ladies or lady, this is the end of our lecture 2. As I told you in the first one, I encourage you to watch this video over and over again. It will help you to really master what you are supposed to learn in this course. And as I have said also, whenever you have any issues, you can contact me on my GSM number. Thank you very much. Until we meet in chapter or lecture number 3. Thank you.